All right, folks. Happy to be here today and talk about spatial analytics and data fusion, design, execution, and benchmarking, the Apache Sedona story. So first of all, about myself, my name is Jia. I'm a co-founder of Wearables, and I started this project called Apache Sedona about 10 years ago, while I was doing my PhD at ASU. So today I'm the PMC chair of Apache Sedona, and I also co-founded Wearables. So Wearables is a company that is commercializing the whole ecosystem around Apache Sedona, and we position ourselves as the spatial intelligence cloud for the real physical world. And so prior to that, I spent a couple years at Washington State University as a faculty member. And my research has been always focused on spatial data management and database systems, and which is something we're going to talk about today. And you can also find me on GitHub, and you can also find me on LinkedIn, and I also have a personal homepage. Now let's briefly introduce a little bit about Apache Sedona. So quick context. So Sedona is a Apache top level project. So it has, well, the font is pretty small. So the overall downloads of Sedona has almost reached 70 millions in total. And its monthly download is over 2 millions right now. So we have users from JP Morgan Chase, Uber, Meta, Allstate, many different companies from actually widely different industrial sectors. And the Sedona ecosystem is actually a family of engines. So we have Sedona Spark, that is for distributed batch processing. We also have Sedona Flink for distributed stream processing. We also have Sedona Snow, which is built on top of Snowflake. And we also have Sedona DB, which is a star out today. So it is our single node analytics engine that is on top of DataFusion. And finally, we also have Spatial Bench. It is also a project under Apache Sedona. It is an open benchmark that ties them all together. I will talk about Spatial Bench as well. So Spatial Bench actually also leverage DataFusion. So Spatial Bench has a data generator. It also leverage DataFusion's TVCH data generator to generate synthetic data for the benchmark. Okay. So first of all, why Sedona DB? So Sedona DB is so first of all, on the left, right? So Sedona DB is designed to handle laptop scale data, laptop scale geospatial data. So on the left, you can see that right now there are users today, they can pick up GeoPandas, which is pretty easy to use, and also it has very strong geospatial support. But the problem is that so GeoPandas, although it is pretty mature, it still failed at handling tens of millions of rows. And we also have DuckDB Spatial, which is pretty fast, but it has very shallow geospatial coverage, and there's no coordinate reference system support and raster support. We also have Sedona Spark, which is overkill. It is a distributed cluster, right? In many cases, you don't need that for your laptop scale data. So Sedona DB fills that gap. It is a single node engine. It uses Rust and Arrow, right? And we also treat geospatial data as the first-class citizen. On the right, this is about why we picked DataFusion. So Rust, Arrow, all the things we love, right? But on the other hand, what matters to us is it also has very extensible logical and physical planner. And Andrew mentioned that all over today, right? So in DataFusion, there are lots of places you can hack, you can extend, so that enable us to have very good support for geospatial data at different places. And of course, the SQL data frame front end and the different language bindings, including Python. And it also have a very strong ecosystem, right? Good support for Parquet, object store. And of course, a very strong community, right? Like you guys. Design. So I'll briefly talk about the design we have in DB. So there are lots of pieces we implement into DB, but today I'm just going to briefly talk about that. So first of all, in DB, we have a couple different spatial data types. So geometry, geography. Some of you probably have heard of my talk before in Iceberg Meetup and Iceberg Summit and Databricks Summit as well. I talked a lot about geometry and geography data support. So this is part of the spatial type we have in DB. But in addition to that, we also have raster support, ND array support, and point cloud support, which is LiDAR. So this is enable us to support a variety of different use cases. So we also have CRS propagation. So this is probably a very domain-specific term. It is called coordinate reference system support. It tells you how accurate your data is on top of the surface of the Earth. And we also have very good spatial optimizer rule support, different optimization rules, including heuristic rules, physical planning rules, and different query operators, spatial join, key nearest neighbor join, range query, Zuno statistics for raster data. We also have buffer pool, and it has a memory budget and also allows you to do disk spill as well. We also have GPU execution support. So this is something that's going to be released in the upcoming version of DB. So we added GPU support for a GPU acceleration for our spatial join. I'm going to talk about that a little bit. And we also have ecosystem hooks thanks to Arrow, right? We can support easy interoperability with GeoPandas, PyArrow, DuckDB, and Polars as well. Cool. Regarding the three data types we talked about, right? So we support vector data, raster data, which is for Earth observation, satellites, and drones. And we also have point cloud data support data type. So it is for self-driving cars. So for vector data, right? Many of you probably already have seen this multiple times. So vector data or vector geometry data, it is not the AI vector, right? This vector means the geometry shapes. So these are points, line strings, polygons, right? So they represent physical objects of the planet. So for our vector geometry support, we follow the standard called OGC, Simple Feature Standard. So basically, it tells you how to encode the geometries. In particular, we use a standard called WKB, well-known binary, which is actually not that well-known, right? Yeah. Also, we also follow another standard for Arrow, which is called GeoArrow. So it is an extension on top of Apache Arrow as well. So we have CRS propagated per column, actually per record. Yes, this is about vector geometry. And you can do some cool things on top of the vector geometry data type. So here is an example about the SQL interface we have for the vector geometry. So you can see that the geometry, they're treated as the first class arrow data type. And you can run some funny operators on top of that. In this example, you have this operator called st within, which is here, this one. And basically, you can use this kind of query operator to find out what are the buildings that is close to your location. You can also find out what are the vehicles that are within a certain census block, right? So on and so forth. And you can also use CRS to have better and more accurate location and spatial predicate definition. And right now in our vector support, we have implemented over 100 ST functions, and we also have geography function operator support. Okay, so the geometry data type, which is actually quite common nowadays, right? So you have that in Parquet, in Iceberg recently. But now I'm going to talk about the two additional data types we have, which are pretty unique inside DB. So the first one is the raster data type support. So this is still work in progress, but we're going to release that in the next version of DB, which is going to be released in 1 or 2 months. So that is the raster data. Oftentimes people refer that as the Earth observation data or satellite imagery data, right? So this include, elevation. This can support lots of different use cases, including elevation, land cover detection, suitability detection, lots of different cool things. So in DB, so this is raster data is treated as a first-class data type. We have native query optimization support and query execution support. So the data input format could be from the original satellite data format, including GeoTIFF or cloud optimized GeoTIFF as well. And we also support several others different format, but basically most of the current satellite data, they were originally supported in this thing called GeoTIFF format. And you can also see this SQL statement up there, right? You can use SedonDB to read data directly from the original raster from the object store, which is the data is originally stored in GeoTIFF format, and then you can run operation on top of that. So there are two operators you can see there. One operator is called RS map algebra. Another operator is called RS Juno statistics. So they are very domain-specific operators, but essentially what it does is that it figures out statistics of an image, for example, so the average pixel values within a certain region, and the pixel values you see on the images on the left. So oftentimes they are referring to a specific spatial observation or Earth observation at locations like rainfall, temperature, land surface temperature, right? By doing those kind of statistic and map algebra operations on those satellite images, that enables you to figure out, to have better understanding of insights of the planet, of the Earth. So now you're able to do all that on top of SedonDB. Another cool thing we did in SedonDB is that so all the data type for raster data, so they are lazy load. So meaning that we never actually eagerly load any raster data directly from the object store. So we only process the image, process the pixel when the actual operator needs the individual pixels. So we call this lazy mode. Okay, I'm gonna jump to this one. Another cool thing we did in SedonDB is that so we also extended the raster data to support ND array, multi-dimensional array, because in many cases the satellite imagery data is really n-dimensional. So it includes time, longitude, latitude, as well as band. So this is more than just like X and Y regular, image pixel, right? So there are lots of complex design behind scene, but we managed to support that, and we build our ND array support on top of a format called ZAR. So ZAR format is in particular designed for this kind of scientific hyperdimension data store. So I'm gonna be really quick, jump to another part. Another data type we have is the point cloud LiDAR support. Again, this is also a new feature we are working on. So this is going to be also released very soon in the next version of SedonDB, is the point cloud LiDAR support. So many of you probably already heard of LiDAR data, right? So nowadays, if you have a self-driving cars, right, you have LiDAR on top of the car, and it's capturing data all the time. It is massive. But many of those LiDAR data, they're actually geospatial data. It has like 3-dimensionality, right? So in SedonDB, right, we have a reader that enables SedonDB to read native LiDAR data from object store, LAS and LAZ format. And we also added support for spatial filtering, spatial relationship check and aggregation on billions of points instead of stored in LiDAR data. Okay. Now let me briefly talk about the execution inside SedonDB. So there are, as I mentioned before, so there are a couple cool features we developed in SedonDB, right? Today I'm just gonna quickly go through a few interesting features that might be interesting to you guys. One is the font is pretty For some reason, it's pretty small. Okay. Anyway, so we recently introduced the GPU accelerated spatial join, right? So many of you probably have heard of like GPU accelerated query processing. There is a QDF, right? So NVIDIA is pushing pretty hard on that, and there is also there's a rapid project from NVIDIA, right? Try to accelerate Spark through GPU, but it turns out it is not that easy to actually accelerate geospatial operations through GPU. The reason is as follows. So the geospatial operation, especially the spatial relationship check, like a pointing polygon, intersect polygon, all these operations, they cannot be easily parallelized to CUDA cores. So if you look at the NVIDIA ecosystem, so there was a project called Spatial. There is QDF, right? There is also a project called Spatial. It is that because you need a totally different design for spatial operation if you want to have efficient processing, spatial query processing on top of GPU. That project is that because it is oftentimes not as fast as the CPU spatial query processing. So in SadonaDB, so we added support for added GPU support for spatial join through a different paradigm. So we enable our GPU acceleration through not CUDA core. We did that through something called ray tracing core. So the ray tracing, so there are a whole bunch of nuance behind the scene, but basically if you play games, right? So the ray tracing core is oftentimes used to do ray tracing so you have like more realistic view in your games, right? So this is very similar to the spatial processing problem we have in spatial join. So essentially we are able to map the spatial relationship check to a ray tracing problem, right? And then we build the index for ray tracing on top of the RT core in NVIDIA GPU. And here is the performance number on our array. So basically, we're able to suppose you have a GPU that has similar cost as the GPU. So we're able to see 7x speed up for spatial join query processing. Okay. Another part I want to briefly talk about is how we execute the raster data, so which is the satellite imagery data we mentioned before, also the ND array data. So the input data, as I mentioned before, they are array data, right? So the way we process that is, so when we actually load the pixels, right? So we put them into small tiles, and each CPU core take a tile, and you have many CPU cores, right? So then they are able to take one core at a time, take one tile at a time, and do the query processing there. That's the raster data processing. Another cool features we recently added is the larger than memory spatial join. This is already released in our last version of SadonaDB. So, you know, in many cases, you're going to do a join, right? For regular join, you have sort merge join, hash join, right? Lots of cool algorithm. For spatial joins, really there is a very popular algorithm called index loop join. So you have two side of join, right? You build a spatial index on one side of join, then you loop over that index. But the problem is that oftentimes both sides of the join is large, right? You cannot just simply build the index on one side of the table and that will go out of memory, and then you won't be able to do anything. So basically, in SadonaDB, we build something called spillable spatial index, or spillable spatial join. So when you build a spatial index on one side of the table, so we try to be respectful to the memory budget. So if the index is larger than the memory, so we're going to start to spill to disk. We build a bunch of temporary files in arrow IPC format. And once that part is done, we go through this probe phase, which is the phase that you actually run the spatial join. So you take the other side of the table, you try to probe against this spillable index, right? Of course, it happens in parallel way. So you could also have multiple CPU cores that try to probe this spillable index. And so the spillable index will try to fetch different small tiles from disk and fetch that into memory. So that's the large than memory spatial join we have. Okay. The final piece I want to talk about is the benchmark, right? So we talk about lots of cool features inside SaddleDB, right? But how could we prove that? So, you know, in regular database benchmarks, there is TBCH, there is TBC DS, there is also ClickBench, right? YCSB, lots of cool benchmark. But in fact, in the geospatial database areas, there's no such thing, right? There's no established standard that can actually measure the spatial query performance, right? So that's why we designed this thing called Spatial Bench. So and this enables us to have a open and reproducible benchmark for across different systems. So in Spatial Bench, we developed 12 SQL queries so far, and we are actually adding more queries for raster data and point cloud data as well. So we also offer different scale factor, 1, 10, 100, so on and so forth, very similar to TBCH. And our design of Spatial Bench is modeled off the star schema. If you heard of TBCH before, so you probably also heard of what is called the star schema benchmark, right? So basically, it is a simplified version of TBCH, and we extend that with spatial attribute, and we follow a particular taxi company example to introduce this kind of taxi trip data into this star schema. Okay. So we also have a data generator for Spatial Bench. So this data generator is forked from DataFusion's TBCH Gen RS. So use Rust, it is deterministic, it also parallel. And it inherits TBCH customer orders line item table, right? Of course, because we are using a different use case, so we change the name and column tabs of those tables, right? And we added a bunch of spatial extension to that. So the geometry columns like boundaries of some polygon zones, some buildings, and also the pickup location, drop-off location of your taxi trips. And we also have realistic coordinate distributions. We have data skewness, and those data skewness actually follows the realistic geospatial locations. Like New York City will have dense taxi trip, but if you are somewhere in Idaho, right? So you probably have sparse taxi trips. And the result is stored in GeoParquet. And we also introduced multi-part output support. The data generator can directly generate data to S3 for like scale factor 100 or scale factor 1,000. So a quick demo about the result we have so far. So this is a benchmark we did last year in September or October. And we compare SaddleDB, the first version of SaddleDB against DuckDB 1.4. And as you can see, we run that on all 12 queries on Spatial Bench scale factor 1 and scale factor 10, which we call laptop scale geospatial data queries. So as you can see here, so we also have GeoPandas there, right? So GeoPandas is like the slowest on all queries, right, at different scale factor. And DuckDB is pretty good and has really good performance, right? And SaddleDB is actually the only engine that is able to finish all queries on all scale factor. So SaddleDB, DuckDB is doing great on scale factor 1, but when it comes to scale factor 10, which is still laptop scale, right? It's like 10 GB data. So DuckDB start to have problems, right? So especially when it comes to query 9, query 10, and query 11. So those are actually spatial join queries that requires join reordering and some sort of query optimization. So DuckDB is not able to finish. So we recently also did a benchmark on DuckDB 1.5. This is a new version of DuckDB if you have been following DuckDB progress, right? So for some reason, it is doing worse. Right now, DuckDB cannot even finish on scale factor 1, query 10 and 11. Cool. This is a benchmark number. Okay, so takeaways, right? Let me just quickly pop this up. So takeaways, right? So we designed SaddleDB on top of DataFusion with different spatial data types. And we have query execution tricks like GPU accelerate spatial join, auto-core spill, and spatial query optimization. And we also benchmark the performance of SentinelDB through something called Spatial Bench. Cool, that's all I have today.